Okay, let's look at problem number 4. Okay, so we're going to talk a little bit about personal grooming. So we have a random sample, that's n, small n of 25, with a sample mean, that's x bar of 5834, and a population standard deviation, sigma, of $14. Since we have the population standard deviation, we're doing a hypothesis test, that means we're going to be using a z-test. Z-test and population standard deviation go together. So we'll know if we have enough evidence to conclude that the population mean is over 50, and so we're going to write our research and null hypotheses. And a research hypothesis is the population mean over 50 translates to mu greater than 50. And our null hypothesis, mu equal to 50, that's what it'll look like on our sampling distribution when we show the p-value. Or we could put the complement of the research hypothesis, mu less than or equal to 50. Because if we reject HO and conclude HR is true, we will have rejected any of the other hypotheses where the population mean is less than 50 as well. So now we're going to evaluate those hypotheses using the critical value approach. So we're going to reject HO if z-test is greater than 2.326. HO was mu greater than 50, so it's one-tailed greater than here. The 2.326 comes from either from the z-table or the bottom of the t-table, the bottom row where we have z-values with alpha equal 0.01 on a one-tailed test. Since we're doing a hypothesis test, we need to calculate first the standard error, which is the standard deviation, in this case the population standard deviation sigma divided by the square root of n. That comes out to be 2.8. And then our z-test is equal to statistic x bar minus the hypothesized mean over the standard error. And that all comes out to be 2.98, which of course is greater than 2.326. So we're going to reject HO and conclude that we can be confident that the population mean is over $50. Okay, let's look at the chart here. You can see we have the sampling distribution, the axis labeled with x bar. We have our hypothesized population mean of 50 with the standard error equal to 2.8. Then there's the specific value of x bar, 5834, that we found in this particular sample. From the previous part, we know the z-test is 2.98. That is, that the distance between the sample mean, 5834, and the hypothesized population mean of 50 is 2.98 standard errors. Z is equal to 2.98. So we're going to look that up on the z-table, and the corresponding probability is 0.4986. Again, that's from 50 to 5834. The p-value is the area out in the tail. So we're going to have to subtract that 4986 from 0.5 to get a p-value of 0.0014. For 4D, first we want to have a practical interpretation. And we're going to reject HO anytime the p-value is less than the specified level of significance. In this case, if the p-value is less than 0.01. We calculated a p-value of 0.0014. That is less than 0.01, so we're going to reject HO. In a more theoretical explanation, if the population mean really is 50, then there is a 0.0014 chance of obtaining a sample mean greater than or equal to 5834. If you look at the graph on the previous page, you'll see the population mean is 50, the sample mean is 5834, and if we get greater than or equal to 58.34, we have a probability of 0.0014. Hence, we're going to reject HO because getting a statistic, a sample mean in this case, of 5834 or greater will almost never occur when the population mean really is 50, and that's what we had in our HO. Again, therefore we reject HO.